Go find a rubber band. Right now. I'm not kidding. Don't just sit there and listen to me talk. Physics isn't something you read about in a dusty book. It's something you feel in your fingertips. Take that rubber band. Hold it against your upper lip. The skin there is very sensitive to temperature, and stretch it quickly. What do you feel? It gets hot. It's a distinct, unmistakable warmth. Now hold it in that stretched position for a second, let it settle, and then let it snap back to its original size. What happens? It gets cold. It feels like a tiny, rubbery refrigerator just touched your face. Now, wait. Think about that. This should bother you. This should keep you up at night. In almost every other part of your physical experience, when you expand something, it cools down. If you spray a can of deodorant, the gas expands and the can gets freezing cold. If you look at the great laws of the universe, expansion is usually associated with cooling. But here is this lowly piece of rubber, sitting on your desk, defying your common sense. By pulling it, by putting energy into it, you are creating heat. By letting it go, you are creating a chill. Why? Is the rubber band broken? Is it disobeying the laws of the world? No. Nature is never broken. She is always honest. It's our intuition that is clumsy. To understand why this rubber band is acting like a thermodynamic rebel, we have to stop looking at the rubber and start looking at the very structure of order and chaos. We have to understand that we live in a world where everything is jiggling, always jiggling, and that this jiggling is the secret key to the entire machinery of existence. To get there, we have to look at the first great avalanche of discovery regarding the hidden internal life of matter. We have to go back to the moment we realized that the stuff we see is just a front for a much more violent, microscopic reality. Let's look at a simpler mystery, the air in your room. If you leave a garden hose out in the sun, the water inside gets hot. Why? Because the sun is beating down on it. But back in the 1800s, people like Daniel Bernoulli and later James Clerk Maxwell began to ask, what is heat really? They didn't have microscopes powerful enough to see atoms, but they had logic. They realized that if you have a gas inside a container and you shrink that container, you compress the gas, it gets hot. Newton's laws of gravity told us how the big things moved, how the moon stayed in the sky by falling precisely 1/20th of an inch every second. But Newton's laws didn't seem to explain why a piston gets hot when you push it. Bernoulli had this beautiful, simple idea. He said, imagine the gas is made of billions of tiny, hard billiard balls particles flying around at incredible speeds, slamming into the walls of the container. That pushing they do is what we call pressure. And the speed at which they fly, that is what we call temperature. Think about a ping pong paddle. If the paddle is stationary and a ball hits it, the ball bounces back with the same speed. But if you move the paddle forward to meet the ball, if you stretch the energy into the system, the ball flies back much faster. You've given it energy. In a gas, when you push a piston in, you are moving the paddle toward the balls. They hit the moving wall and bounce back faster. They jiggle harder. And because they jiggle harder, the temperature goes up. This was the first great bridge. It connected the earthly experience of heat to the mechanical laws of motion. It told us that heat isn't some magical fluid called caloric. It's just the kinetic energy of the jiggling. It's an avalanche of logic that says, if you want to know the temperature, count the jiggles. But then we come back to our rubber band. If stretching a rubber band is like expanding its internal structure, shouldn't the particles have more room to move? Shouldn't they slow down and get colder, just like the gas in a cooling refrigerator? This is the brutal challenge to your common sense. The rubber band isn't a gas, it's a solid, or at least it looks like one. But it's acting in a way that seems to flip the rules of the piston upside down. To solve this, we have to realize that a rubber band isn't just a collection of billiard balls. It is a tangled, chaotic mess of long, stringy molecules. We are moving from the simple world of Newton's falling moon into the messy, complicated world of entropy. We are moving from the order of a single rock falling in a garden to the chaos of a billion microscopic chains being tugged into a straight line. Before we can see why the jiggling makes it hot, we have to understand the history of how we discovered that the universe has a direction, that it prefers chaos over order, and that it will fight you every step of the way if you try to organize it. So, we've got this piston filled with gas, and we understand that when we push it in, the jiggling increases and things get hot. That's ordinary physics. But the rubber band is doing something that feels backwards. To understand the twist, we have to move away from the simple billiard balls of Bernoulli and into the strange, tangled forest of polymers. Wait. Think about what a rubber band actually is. It's not a solid crystal like a diamond or a piece of iron. If you look at a piece of iron, the atoms are lined up in perfect military rows. They are locked in place. But rubber is made of long, spaghetti-like chains of carbon and hydrogen molecules called polymers. In their natural, relaxed state, these chains aren't straight. They are a mess. They are curled, kinked, and tangled up like a bowl of yarn that a cat has been playing with for 3 days. Now, here is the mystery that broke our old understanding of solids. In the mid-1800s, scientists like Lord Kelvin and James Prescott Joule, the man who proved that work and heat are the same thing, started measuring rubber. They noticed something that defied Newton's absolute clockwork world. They found that if you take a weight, hang it from a rubber band, and then heat up the rubber with a flame, the rubber band doesn't expand like a metal wire would. It contracts. It pulls the weight up. Think about that. Almost every material in the world expands when it gets hot. Bridge joints have gaps because the steel grows in the summer. But rubber, you give it heat and it shrinks. This was the historical aha moment. It told us that rubber isn't being held together by the same kind of atomic glue as a piece of steel. It's being held together by entropy. To understand entropy, we have to look at the numbers of chaos. Imagine you have a single long chain of rubber. There is only one way for that chain to be perfectly straight. You pull it tight. One configuration. But how many ways are there for that chain to be a tangled, messy ball? Millions, billions, an astronomical number of ways. Nature loves big numbers. Nature is a gambler that always bets on the outcome with the most possibilities. This is the second law of thermodynamics. The universe always moves toward a state of higher disorder or higher entropy. The rubber band wants to be a tangled mess, because being a mess is more probable than being a straight line. Now, let's look at the experiment that Joule performed. When you stretch that rubber band, what are you actually doing? You are forcing those chaotic, jiggling chains to straighten out. You are taking a billion messy piles of yarn and forcing them into neat, parallel rows. You are creating order. But the universe doesn't like order. The universe wants to stay jiggling. As you pull the rubber band, the molecules are fighting you not because of a spring force, but because they are constantly being hit by the thermal jiggling of the atoms around them. When you force the chains to straighten, they lose their ability to wiggle in as many ways. That wiggle energy, that kinetic energy of the jiggling, has nowhere else to go. So it gets dumped out of the molecules and into the surrounding material. That is why your lip feels heat. You are literally feeling the cost of creating order. You are feeling the energy being kicked out of the molecular chains as you force them to stop their chaotic dance. You are turning order into heat, and when you let go, the chains suddenly have the freedom to be messy again. But to become messy, to start jiggling and tangling back up, they need energy. Where do they get it? They suck it in from the environment. They steal the heat from your lip to fuel their return to chaos, and that is why it feels cold. This was a total flip in how we thought about matter. We realized that solidity isn't just about atoms sitting still. It's about a constant, violent war between the energy you put in and the natural desire of the universe to be a mess. We move from the absolute space of Newton to a statistical world where heat and information are the same thing. Stretching a rubber band is like erasing information. You are taking a complex, chaotic system and forcing it into a simple, predictable state. And in this universe, erasing information always has a temperature. But how deep does this go? Is it just rubber? Or is this entropic force the secret behind everything, from the way your DNA folds to the way the stars eventually burn out? To see the why behind the how, we have to look at the layers of reality. Now we're getting to the deep physics. You've felt the heat on your lip, and we've talked about the tangled yarn of molecules. But to truly understand the truth with a capital T, we have to look at the world through three different lenses. We have to peel back the layers of reality until we see the machinery that connects a rubber band to the very heart of the cosmos. The first layer is the physical action, the molecular tug of war. Think about what's happening in that rubber when you pull it. Inside, there are these long, winding polymer chains, mostly made of carbon atoms linked together. In a normal solid, like a crystal of salt, the atoms are bonded in a rigid grid. If you pull on a salt crystal, you're trying to stretch the actual chemical bonds. That's why salt is hard and brittle. It doesn't want to budge. But rubber is different. It's a cross-linked mess. The chains are long and floppy, but they are tied together at certain points. When you stretch the rubber band, you aren't stretching the bonds between the atoms, at least not at first. You are simply uncoiling the chains. You are taking something that looks like a pile of cooked spaghetti and trying to pull it into a bunch of straight, parallel lines. Here's the kicker. As those chains straighten out, they start to vibrate against each other. They are jiggling violently. Because they are now packed closer together and aligned, they bump into their neighbors more frequently. This increased bumping is what we perceive as a rise in temperature. The internal energy hasn't necessarily increased, but the type of energy has shifted from potential to freedom to be tangled into kinetic, the motion of bumping. The second layer is the mind break, the force of pure probability. Now, hold on. Here is where your brain should start to itch. If I tell you that a weight is being lifted by a spring, you say, okay, there's a force there. But in a rubber band, the force that makes it want to snap back isn't a pulling force in the way you think. It is a statistical force. In physics, we call this an entropic force. Think about it. A stretched rubber band wants to contract. Why? Because there are billions of ways for it to be a mess, and only one way for it to be straight. It's like a deck of cards. If you throw a deck of cards in the air, they don't land in perfect numerical order. Not because they hate being in order, but because there are just so many more ways to be disordered. The force you feel pulling back on your hand is literally the universe's overwhelming mathematical preference for chaos. You aren't fighting matter. You are fighting probability. This is the mind break. In a rubber band, entropy is acting as a spring. Most people think entropy is just about things falling apart or getting old. But here, entropy is doing work. It's pulling. It's holding things together. It is a creative, structural force born entirely out of the jiggling of atoms. The third layer is the cosmic connection, the universe's one-way street. Wait, let's go even higher. This little rubber band experiment is a microscopic version of the entire history of the universe. The second law of thermodynamics says that the total entropy of the universe must always increase. When you stretch the rubber band, you are creating a tiny pocket of order, or low entropy. But the universe demands a tax for that order. That tax is the heat you feel. By making the rubber band more ordered, you are forced to make the rest of the room disordered by dumping heat into it. You cannot create order without paying for it in heat. This is the avalanche of discovery that leads to the heat death of the universe. Every time you stretch a rubber band, every time you take a breath, every time a star burns, the universe is moving toward a state where everything is perfectly jiggled, perfectly messy, and perfectly cold. The heat on your lip is a tiny echo of the cosmic furnace. You are feeling the arrow of time in a piece of office stationery. We've moved from the absolute laws of Newton, where everything was reversible, to a world that has a clear direction. A world where jiggling isn't just a byproduct, it's the master of the house. But how do we know this is the real story? Is there proof that this statistical jiggling is what's actually happening? To find the final proof, we have to look at how we've used these same laws to build everything from refrigerators to the most advanced sensors in the world, and reflect on what it means to be a part of this chaotic, beautiful machine. Now, you might be asking, Feynman, this is all very clever statistical forces and molecular spaghetti, but do we have any hard proof, or is this just a fancy way of telling a story? In science, we don't believe in stories. We believe in things we can measure, things we can repeat, and things that predict the future. And the proof for this entropic force is everywhere around you. Look at the refrigerator in your kitchen. It is a miraculous machine that operates on the exact same principles you just felt on your lip. When the fridge compresses a gas, it forces the molecules to jiggle harder, creating heat, just like stretching the rubber band. It then dumps that heat out the back through those cooling coils. When the gas is allowed to expand again, it sucks in heat from inside the fridge to fuel its return to chaos, making your milk cold. Your simple rubber band is a miniature heat engine, a testament to the unity of physical laws from office supplies to high technology. But there is another proof, deeper and more biological, your own DNA. DNA isn't just a rigid ladder. It's a massive polymer chain floating in a sea of jiggling water molecules. When the proteins in your cells need to read your genetic code, they have to stretch or coil these DNA strands. Scientists have performed single molecule stretching experiments, and guess what they found? They found the exact same entropic laws we found in the rubber band. Life exists because it has mastered the art of playing with these statistical forces. You aren't just observing physics, you are physics. Wait. Let's stop for a second and look at the big picture. We started with a silly question about why a piece of rubber gets warm. And we ended at the very frontier of our understanding of the universe. What does this tell us? It tells us that nature doesn't divide the world into rubber band physics, DNA physics, or star physics. It is one game played on one chessboard. Those tiny jiggling particles don't know if they are inside a piece of rubber or the core of a burning star. They just follow the rules of motion and probability. There is a profound beauty in this chaos. Many people fear the word entropy because they think it means destruction, the death of the universe. But think of it this way. Without entropy, without that chaotic jiggling, the world would be a frozen, lifeless crystal. It is the very desire of matter to become messy that creates the flexibility of rubber, the movement of your muscles, and the life in your cells. The warming of the rubber band is a reminder that we live in a dynamic universe where order is a precious thing that must be paid for with energy. We are islands of order in a sea of chaos. Every time you think, every time you learn something new, you are creating order in your brain, and you are literally radiating heat out into the world to pay for it. I hope the next time you pick up a rubber band, you won't see it as a dead object. See it as a map to the deepest secrets of thermodynamics. Feel that warmth and remember that you are touching the arrow of time. This world is never boring if you know how to ask the right questions. The truth is always there, hidden behind the most mundane things, waiting for someone curious enough to look past the surface. The great chessboard is still there, and every why is a move that brings you closer to understanding the mind of nature. So, are you ready to find out what time really is? Or why the night sky is pitch black despite the infinite stars? The journey has only just begun.